Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion. In this lecture, what I would like to do is work through a bit more challenging exercise. You might recall what we've been talking about. We've been looking at Chapter 10 in A Student's Guide to the Great Physics Text, Volume 2, and in this chapter, Galileo is discussing the force that is required to hold an object stationary on an inclined plane or on a ramp. And then he talks about the acceleration that this object will feel if that force is removed and it's allowed to slide down the ramp. So let me set up the problem in this way. Let's suppose that we consider two ramps side by side. One we will call the left ramp, and one we will call the right ramp. And these two ramps, we'll say, have different slopes. The one on the left is a steeper ramp than the one on the left. And let's suppose that these ramps are just the right angle so that the ratio of the sides of the ramp on the left are 1 to 1 to root 2. So you might see that as a 45, 45, 90 triangle. And the ramp on the right is 1 to root 3. Okay, so that is a 30, 60, 90 triangle. And let's suppose we have a pulley at the top of each ramp, like this. And let's suppose that we place a block on each ramp. And importantly, we're going to claim that these two blocks have the exact same weight. So each of them has a weight of 1. That could be 1 pound or 1 newton, whatever units you would like. The important thing is that they have the same weight. And now we're going to ask what weight must be suspended from each of these two ramps, from each of these two pulleys, so as to support these two weights. So if we have a string passing over here and a string passing over here, what is the weight that's required to support the block on the left ramp, and what is the weight that's required to support the block on the right ramp? So we'll call this right here, we'll call this weight C, and we'll call this weight D. So the first question, question 1, is which requires a larger counterweight? In order to remain stationary. And you can probably guess this without doing any calculations. Since both weights have a weight of 1, and since the ramp on the left is steeper, the block on the left is going to require a larger counterweight in order to hold it stationary. And the block on the right is going to require a smaller counterweight. In other words, the answer to question 1 is that the weight of block C is going to have to be larger than the weight of block D. You probably sense this intuitively to be correct. So let's be a little bit more precise now. The next question is, what are the values, or what are the required values of the weight of block C and the weight of block D? Well, we have a strategy for doing this. We came across it in our last lecture, and that is that the ratio of the weights, weight 1 and weight C, is in the same ratio as the length of the line segments, that is root 2 to 1. So if I were to write that as the weight C is to 1, that's the ratio of the weight hanging from the left pulley and the weight sitting on the left ramp, that has to be in the same ratio as 1 over root 2. Or in other words, that the weight of block C is 1 over the square root of 2. And what about on the right? Well, similarly, the weight of block D is to the weight sitting on the ramp, that is 1, in the same ratio as 1 to 2. That is the length of the line segment length, the vertical line segment length compared to the line segment length of the ramp. Or in other words, the weight of block D is going to be 1/2. So you see right away that weight C, this is consistent with our intuition that the weight of block C is going to be greater than the weight of block D, because 1 over root 2 is bigger than 1 over 2. Okay, let's go on to the next question. Question 3. Which will experience a bigger acceleration when released? So if these two strings are cut and both blocks are allowed to slide down the ramp, which will accelerate more? Well, we know the answer to that. We know intuitively that the block on the left is going to slide down more rapidly because it's a steeper ramp. But it's also, and this is what Galileo was getting at, it's because it took a larger weight to support it. And that's going to give us a strategy for figuring out how much greater the acceleration is. So the left block will have a larger acceleration. Importantly, and we'll come back to this in a moment, they will both undergo a constant or uniform acceleration insofar as the ramps do not have friction. They'll have uniform acceleration, but the values or the magnitudes of those accelerations will be different. Okay, now I'm going to ask the hardest question. So let's suppose I were to tell you that in 1 unit of time, this could be 1 second or 1 heartbeat or whatever unit of time you choose to use, if it takes 1 unit of time for the left block to slide all the way down the ramp, then how much time will it take for the right block to slide all the way down the ramp? So if the left block takes 1 unit of time to descend the ramp, to descend the left ramp. And I know that I've drawn these blocks kind of halfway down, but you might imagine that they're both right at the top of the ramp. Okay, so it takes 1 unit of time to descend the ramp. Then, how many units of time are required for the right block to slide down? This is a bit harder question to answer. Well, the first thing we're going to need to do is to determine, if we want to know how much time it takes, we're going to need to know what the accelerations of these two blocks are. Well, we don't know what the acceleration of either is, but we do know what the ratio of their accelerations is. That is the acceleration that the left block feels compared to the acceleration that the right block feels has to have the same ratio as the force of restraint that the left block had felt in order to hold it up, compared to the force of restraint that the right block had taken to hold it up. And we know what the ratio of those forces are. That is just the weight of C compared to the weight of block D, which we know is 1 over root 2 compared to 1/2. Or, if we simplify that, if we simplify that, it would be 2 divided by root 2. So we know how big the left block's acceleration is compared to the right block's acceleration. And this is going to give us a strategy for figuring out how much time it takes to slide down the ramp. But in order to figure out the time, we need one other piece of information. Well, we do also know a formula for the relationship between the distance an object moves, its acceleration, and the time. So recall that for a uniformly accelerating object, the distance that it moves is equal to 1/2 the acceleration it feels times the time squared, right? Now that is going to give us a strategy for figuring out how much time it takes the right block to slide down. If we invert this formula, and I'll come up here, we can solve for the time in terms of the distance and the acceleration. So if I invert that formula, I will get that the time is equal to 2 distance over a square root. I've simply inverted this formula to get this formula. And now we can find the ratio of the time it takes the right block to slide down compared to the time it takes the left block to slide down. Because after all, we're told the time it takes a left block to slide down. And we can do that in the following way. The ratio of the times is the ratio of twice the distance that the right block slides, I'll use a subscript r for the right block, divided by the acceleration of the right block, divided by twice the distance of the left block divided by the acceleration of the left block. Okay? So I've just formed a ratio using the formula that I just derived a moment ago. Let's simplify this. The time it takes for the right block to slide down divided by the time it takes the left block to slide down is going to be equal to, I'm simplifying the right side now, the acceleration of the left block divided by the acceleration of the right block times the distance that the right block slides divided by the distance that the left block slides. Now look what we have. Well, we have a ratio of accelerations and a ratio of distances, and that allows us to figure out the ratio of the times. We know the ratio of the accelerations. That's what we derived down here. It was 2 over root 2. And we also know the ratio of the distances that it has to slide. Well, the distance that it has to slide in the right case is 2, and the distance that it has to slide in the left case is root 2. So we'll have 2 over root 2. In other words, we will have 4 over 2 square root, or the square root of 2. That is the ratio of the times is root 2. In other words, if it took the left block, like I said, 1 unit of time to slide down, then we'll take the right block, the square root of 2 units of time to slide down the ramp. Now, that's a bit more complicated problem, but it's something that you can do. You just have to think through it carefully. I'd like to say one other thing before I move on, and that is we can find the speeds that these objects have at the bottom. So let me move this out of the way. So the final question, question 5, is what is the speed of each at the bottom? At the bottom. Well, we can find the ratio of the speeds, the velocity that the left block has compared to the velocity that the right block has. And in the case of uniformly accelerated motion, the velocity is linearly proportional to the time, so we could take the acceleration of the left block times the time it took the left block to slide down compared to the acceleration of the right block times the time it takes the right block to slide down. Well, we know the ratio of the accelerations of left to right, and that is just, once again, 2 over root 2. And the ratio of the times, well, that was 1 over root 2. And you get 2 to 2, or in other words, 1. And notice what we're saying here. We're saying that although the right block has a smaller acceleration, it takes a longer time, and those two quantities conspire in such a way that the velocity that the right block has by the time it gets to the bottom is exactly equal to the velocity that the left block has by the time it gets to the bottom. You might recall that's precisely what Galileo said back in figure 8.2 and the chapter 8 of the text, where he mentions that regardless of the slope of the ramp, the blocks will arrive at the bottom with the exact same speed, provided the altitudes of the ramps are the same.